Okay, so here we're going to be talking about finding the equivalent resistance. The equivalent resistance. What is resistance? Like the name suggests, it's anything that resists the flow of current. But of course, like everything else, it can be made useful for current flow and circuits. But we can talk about that in another video. How do you find the equivalent resistance? What does the equivalent resistance mean? It means if you had all these are resistors, I assume that's the prerequisite to do this question. You should know that this is a resistor. There are seven resistors in here. And equivalent resistance just means if you could replace all the 7 resistors with one resistor, just with one resistor, what would the value on that be? So to start off, I would have to assign values to these resistors, or at least it would have to be given to me. To make this a more general solution, I'm going to call them all R. R, 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 R. So it's like the number 2. So say all of them are 2 ohms, or all of them are 5 ohms, or all of them are 10 ohms. And the reason I'm using R to solve for this is if you got the same question or a similar question with any other numbers, you could, use the same logic. I could do it with numbers. Some people find that more easier to follow. Maybe I'll do another video with that too. So first off, when you have to do equivalent resistance questions, the first thing you want to make sure is that you can identify what's in series and what's in parallel. What's in series and what's in parallel. What does series mean? Series means the same current flows through it. So 2 resistors are said to be in series with the same current flows through it. So when I look at this here, first off, where do I start? The left side or the right side? I would start with the right side because the left side is sort of open, a little unsure about what's going on here. Right side is a closed little loop, so we can start there. When I look at this, what is current? Current is just the flow of charges. So somehow there's current flowing through here, whether it's towards the right or the left, we're not sure. We don't know, but it doesn't really matter as long as there's flow some way or the other. And even if there isn't, we could find an equivalent resistance. So let's assume the flow is like this. There's current coming in here because of this point where the path, it's like a path breaks into 2. So you'd have current going this way and you'd have current going this way. But the current that goes this way is this, say if it's like 2 amps or something, whatever the value is, it goes through the R, and that same current comes here. It doesn't have anywhere else to go. So that same total current goes through this R, comes here and goes through this R. So the same current goes through the 3 R's. So these 3 resistors are in series. So I can simplify these 3 resistors here as just one resistance, which is, and when they're in series, what do? You just add the resistances. So you do R plus R plus R. That gives you 3R. Now this is, so instead of all of these resistors here, you can take that out. I'm going to take all of that out. We've already combined 3 resistances into 1, and we know the value of that is 3R. Now you might ask me, why did I draw it this way? Why didn't I draw it, say, over here on top, like somewhere on this part, somewhere on this point here, or so? It just makes it easier to look at it. You could draw it there, it makes no difference. But when I draw it this way, this is 3R and this is R. Now I ask myself, is 3R and R in series or in parallel? Definitely the same current does not flow through both of them because the current comes in like this, and part of that breaks into R and part of it goes into 3R. So it's not the same current that goes into 3R that comes into R. There is a branching off. And so it's probably not in series. What does parallel mean? Parallel means that the 2 ends of both the resistors are connected to each other. So if you look at this resistor here, one end of this resistor is connected to one end of the 3R resistor. And the other end of this resistor is connected to the other end of the 3R resistor. Yes, there's some copper wire in between, but that's just copper wire. There's nothing in between this. There's no resistance or nothing placed that we can see. So by definition, these 2 resistors are in parallel. So when you have a parallel resistor, it's not as simple as adding them up. To combine the two, you have to say, okay, the combined resistance, the combined 1 over the combined resistance is equal to 1 over the first resistance. We call this equivalent resistance. 1 over the first resistance plus 1 over the second resistance. The order doesn't matter because you're adding them. You could have put the 1 over 3R plus 1 over R. It makes no difference. So now, so now we just have to do a little bit of fractional algebra, which we all love. This is your common denominator. So this is 3 times 3. So it's going to be 3 plus 3 over 3R plus 1 over 3R, which is 4 over 3R. And this is 1 over the combination or the combined or the equivalence of these two resistors. So then R equivalence is going to be 3R over 4. Good. So we've come closer. Oh, it's been open the whole time. Okay. So now we go back up here and we ask ourselves, okay, what can we do with this? We can now get rid of these two resistors. Get rid of these two resistors. We can put, and we can draw a resistor here. And that resistor is going to be 3R over 4. So you see, we're slowly working ourselves back. We're cleaning this circuit up. We started with how many? 6, 7 resistors. Now we're down to 5 resistors, if I'm not mistaken. Right. So yeah, we had 6, 7 resistors. Now we're down to 5 resistors. A lot of work to just get rid of 2 resistors, but we're getting there. Again, we ask ourselves, what's going on with these resistors here? I can see there are 3 resistors here. So there's a current that's coming in like this. It breaks over here into 2. And this current that breaks into 2 over here flows like this, flows like this, flows like that, and comes back like this. So it's the 3 resistors together. So they're in series because it's the same current that's going through all of them. So what is the net of that going to be? The sum of the R plus 3R over 4. There's going to be 4R plus 4. 4R plus 4R is 8R, 11R over 4. So all of that's going to be 11R over 4. So I take that all out. So now I combine these 3 and I get 1 resistance for all of that, and that's going to be 11R over 4. Now again, the same logic, 11R over 4 is in parallel with R. So 1 over R, the combination of the 2 resistances, they're in parallel. You can see why they're in parallel. Why are they in parallel? Because like we said, one end of this resistor is connected to the other end of this resistor, and the other end of this resistor is connected to the corresponding other end of the 11R over 4 resistor. So the combined, the equivalent of these two will be 1 over the first resistance, whatever, the order doesn't matter, we said, and 1 over the second resistance, 1 over 11R over 4. And what is the 1 over a fraction? The flip of that fraction. So it's going to be 4 over 11R. It's going to be 1 over R equals 1 over R equivalent. And so we're going to get 5. We're going to get 5 over 11R over 1 over R equivalent. So the net R equivalent is the flip of this, 11R over 5. So then we get finally that these two combine to 11R over 5. So I can write this is just 11R over 5. Finally, these 3 are clearly in series. The current that comes in through here has only one way to go, like that, like that, like that. So the equivalent resistance finally is going to be the sum of the 3, which is R plus plus 11R over 5, which is 5 common denominator. You're going to get 5R, 5. You want to get 5 in the denominator of both. So it'll be 5. This will be 5R over 5. This will be 5R over 5. So we'll get 5 plus 5, 10 plus 11, 21R over 5. And that is the equivalent resistance of this whole circuit. So these 7 resistors, each of value R, we could have just taken all those resistors out and we could have put one resistor of value 21R over 5, and that would have the net effect. They would have the net same effect as putting those 7 resistors. So you could have saved a lot of material. So say each of these resistances were 10 ohms, then you would need take out the 7 10-ohm resistances, and you could put one resistance of 21 times 10 over 5, which is 21 times 2, which is 42 ohms. So instead of wasting your time putting 7 10-ohm resistors, buying 10 ohm resistors, 7 of them, you could just buy one 42-ohm resistor and place that too. And that's the idea behind this. Hope that made sense. Shoot me a question if you have any. All right, have a great day.